All right, now we're going to pick this up looking at the molecular shape and how it affects polarity. And we're starting off with a couple of examples, one especially down here. Now, in terms of polarity, our basic idea again was if there is a difference in, depending on the difference in electronegative values or negativity values, we're going to come up with what's called a polar bond, where these electrons are being shared unequally. Now, while we still have this idea going, we're going to take it a step further and look at in terms of molecules. Before we just looked at single bonds. Now, it's possible for a molecule to contain polar bonds and still not be polar. One of our good examples here is given to us here at the bottom with carbon dioxide. If you pay attention, we know that the values, using our charts, that the value of our oxygen are a little bit larger. So it's actually going to have a slightly negative charge here, as well as a slightly, ran out of space there, negative charge here. Now, in the same breath and at the same point, they're pulling in opposite directions. One of the things that's going to determine whether our molecule is polar or not, or will help us to see if it's polar or not, is when we look at the shape, is there an even pulling, or do we have what's called a center, where we have just positive and just negative on the ends of the atom? We want all the negative to be towards one side and all the positive to be towards one side. This is going to help us to be able to split that difference. Now, if you notice here what we have for carbon dioxide, we have our two different poles, hence the word polar. We have a pole here, we have a pole here. And then the center is where we have our slightly positive charge. Because of this, we're actually going to lose our dipole moment, or cancel out our dipole moment, I would say, so that we end up with a nonpolar molecule, even though it does contain polar bonds. Taking a look at water instead, we have a non-linear compound, and the bond dipoles don't cancel each other out. So if you look at it, and if I was to be able to split this molecule completely through the middle, what you're noticing is I have one end that's going to be positive, slightly positive, and I have another end here that is slightly negative. Again, still one whole side of the molecule is positive, one whole side of the molecule is negative. This gives us that difference in polarity, and even as you see in the diagram here, you're seeing the difference in electron density, how much it's pulling, how strong it is. And this is going to be very, very important as we continue to go through. Now, these are also some examples to make it clearer to see. When we have, of course, our regular single bonds, our diatomic molecules, but examples of hydrochloric acid or different things like that, we know that there's an unequal sharing of the electrons. And so we end up having a clear, distinct, this is one side is positive, this one side is negative. But when we look at examples more like our trigonal planar or our tetrahedral shapes, where everything around them is even, we end up with a different situation. What do I mean? If we look at boron, between boron and fluorine, there is definitely a big difference in electronegativity and the strength. But if you look around it, at each place where a fluorine can bond, 1, 2, 3, you have electrons, each electron being pulled. With this, if this molecule, BF3, boron trifluoride, was to try to interact with something that has a dipole, it does not have the ability to attract on both sides, so it ends up being nonpolar. Whereas if you look at our polar example here, that's a tetrahedral shape, similar to our regular methane that we would look at, you notice that there's a strong pull on one end of the molecule that has a slight negative charge, whereas this whole part then becomes a slightly positive charge, allowing us to see that there is a different and completely opposite pole that we're going to be utilizing. Now, take a few moments, make sure you're digesting this, because we don't want to leave you behind on. I don't want to leave you behind on this concept because it'll come and play out, and we see how it plays out in between acids and bases and different things like that. Now, sorry. Now, why in the world do bonds actually form? And although we do use the term and the statement that atoms want to be stable, we know that they don't have minds of their own, but they tend to do things and behave a certain way in order to become stable. First thing that we look at here is what exactly is a bond. A bond is going to actually form when we have these orbitals that are going to overlap. Now, if you do not remember the information about orbitals, you want to go back, take a little bit of time and review that video so that you can use that as we continue to move forward and you don't have any gaps in the information. But there are two elements, or electrons, of opposite spin in the overlapping orbitals. Basically, the idea that goes back to is with our Pauli exclusion principle. In order for two electrons to inhabit the same amount of space, or the same space, they have to have what's called opposite spin. Now, does that mean that they're actually spinning the opposite direction? Not necessarily, but it's just a way for them to be able to cohabitate within the same space without repelling each other so far apart. Now, these these electrons, as they're interacting within the space, we have this overlap. And so as you see here, with our hydrogen and our chlorine, we have a bonding at the 1s and 3p orbitals. And it's just a slight overlap that's allowing us to be able to see the bond, or the quote-unquote bond that's being formed and shared. Now, does it mean that these electrons are always there? No, it's more that they are moving around within these spaces, but there is some sort of pairing that's being utilized. Now, when these orbitals overlap, it will lower the overall energy of the two atoms, so it becomes more stable. This is the idea, and I say this all the time, and this is my phrase for electrons. Electrons are lazy. Just think about us. If there are stairs, if there's an elevator, many times we'll go towards the elevator because it requires less energy. And the same thing, that's what's going to happen here with our electrons. They're going to try to find the way that is going to take the least amount of energy and allow them to still be stable. So we're looking at our example here of our hydrogen gas, our hydrogen molecule. As the nuclei get too close together, and also the electrons get too close together, we're actually going to get some sort of repelling. But we have also a point where it is key, and you see the change in energy over time. It starts off very high while they're very far apart, and it actually decreases as they get closer until they reach a certain point. In this case, 0.74 angstroms that are being used as the distance. And then as they get further apart, you start to see that energy release. There's a point where that energy is lowest, and that is shown to us right there at that 0.74 angstroms value. Now, we're going to get in the hybrid orbitals in the next video, so make sure you take your time, go back through this, look at your notes, look at your book, and make sure you have these concepts in terms of what an orbital is, how we'll use it, and how they're arranged around the atoms. Have a good evening, and I'll talk to you soon. See you in class.